Last class I promised you guys I'd show you an example of an equilibrium problem where we do not have to solve the quadratic, okay? Where we can use an assumption to avoid the quadratic equation. So this problem is on slide number 48 in the PowerPoint presentation, and it is in equilibrium. It is hydrocyanic acid reacting with water, creating hydronium ions and cyanide ions, and it says the Ka is 4.9 times 10 to the negative 10th. Now you'll notice that says Ka and not Kc. All that means is this is an equilibrium for the dissociation of a weak acid, and we'll learn more about what that means when we start chapter 16 on Monday, but you can treat these Kas just the same as we've been treating Kcs, okay? And then we start off with an initial concentration of 0.1 molar hydrocyanic acid, and we want to know what the equilibrium concentration of cyanide ion is. Okay, so the very first thing you're going to need to do, always, is write a balanced chemical equation. And I gave this to you in the PowerPoint, but I'm going to go ahead and write it here. This is my hydrocyanic acid plus water going to hydronium ion plus cyanide, and the Ka. Okay, so then the second step is to make an ice table, alright? That's initial change in equilibrium concentrations. Now we start off with an initial concentration of hydrocyanic acid, 0.10 molar. We start off with no hydronium and no cyanide. Now the water. Water is a liquid, and in this case we're going to consider it a pure liquid, okay? Yes, there's hydrocyanic acid and there's ions floating around in it, but those concentrations are so low that whatever is happening with these concentrations of these other species is not going to significantly impact the concentration of the water. So the water's concentration is constant, it's built into the equilibrium constant, and we don't have to include it in our ice table, okay? So now, we're only starting off with concentration of product, no reactant, so we know we don't have to calculate Q. We already know which way this reaction is going. This reaction is going to go to produce products. So we don't know how much product, but we know we're going to lose some amount of the cyanic acid, and for every 1 mole of cyanic acid we lose, we gain 1 mole of hydronium ion, and we gain 1 mole of cyanide ion. So if we lose X number of moles of hydrocyanic acid, then we gain X number of moles of hydronium ion and X number of ions of cyanide ion. Okay, so now that's initial and change. Equilibrium concentration is just the initial plus the change. So 0.1 molar plus negative X is 0.10 minus X. 0 plus X is still X, and X. Okay? Now that we have concentrations representing all the equilibrium, representing all the concentrations at equilibrium, we can go ahead and plug these into our equilibrium expression. So let's write an equilibrium expression first of all. Okay? So we're calling this Ka, but it works just like any Kc. Okay? It's always products. There's a hydronium ion and cyanide over reactants, and the coefficient in the chemical equation here, these are all 1s, so we don't have to raise these to any powers. Okay, so now we can go ahead and plug in these representations for equilibrium concentrations from our ice table. So hydronium ion is going to be X, cyanide ion also X. X times X is X squared divided by 0.10 minus X. We're setting that all equal to 4.9 times 10 to the negative 10th, because that's our equilibrium constant. Okay, so this looks a lot like the problem we did last class, right? You've got X squared, you've got X's, and you're well on your way to having to solve a quadratic equation, right? But if you sit and look at these numbers, Ka is a very, very small number. 4.9 times 10 to the negative 10th. That's a very, very small number. and that is equal to products over reactants. So that tells you that the amount of products being formed here is very, very small. If your amount of product is being formed is very, very small, then when you look at here, at 0.1 minus the amount of product formed, really that x may not be significant, okay? Think about it this way. What if your x was equal to 0.00006, okay? Well, 0.1 minus 0.00006 is still 0.1, right? To the amount of significant figures we're looking at, it really doesn't make a difference at all. So we're going to make an assumption that this x is so small, it doesn't make a difference to the value of 0.1 molar. And we're just going to cross it out. Okay? Now, anytime you make an assumption like this, when you get to the end and you get your final answer, you need to go back and make sure your assumption was valid. Okay? Make sure it really was okay to cross that off, that it was insignificant compared to the 0.1 molar. Okay? But for right now, we're just going to cross it off, pretend it doesn't exist. So then we can do 0.1 times 4.9 times 10 to the negative 10th. Right? That gives us 4.9 times 10 to the negative 11th equals x squared. We take the square root of both sides, and x equals 7.0 times 10 to the negative 6 molar. Okay? And so that means, if you go back and look, our original problem said, what's the concentration of cyanide ion? Well, the concentration of cyanide ion at equilibrium is 7.0 times 10 to the negative 6 molar. Okay? So that's our answer. But before we're finished, we have to go back and make sure our assumption was valid. Okay? Our assumption was that the amount you were subtracting for 0.1 molar would be insignificant compared to the 0.1 molar. Okay? Now, anytime you make that sort of assumption, you're introducing a small amount of error. And so the question is that amount of error going to make a difference? Is that amount of error to a level that's acceptable for you? Different books or different people who have different purposes can accept different levels of error. Your book has a 5% rule, and so we're going to go with the 5% rule. And what the 5% rule says is that if the amount of x is less than 5% of what it's being subtracted from, then the amount of error is acceptable and the assumption was valid. You could disregard x. Okay? So the amount of x here, 7.0 times 10 to the negative 6 molar, divided by 0.10 molar times 100%. Right? And that ends up being 0.007%. So what this tells you is that amount of x was 0.007% of 0.1 molar. So that is definitely an acceptable amount of error, right? Anything less than 5%, we're going to say that's an acceptable amount of error, and it's a legitimate thing to make that assumption.